All right, we're going to do a quick block of instruction on tolerances. This is a topic in engineering, particularly in manufacturing, that's important because it helps you to describe just how specific you need to be with regard to how you make your parts. Okay, so let's keep rolling. Right, so you are going to have variation in your manufacturing processes, or if you're in Canada, it will be processes. So we're going to talk about how we manage your variation. There's a certain amount of variation that's allowable, and certain when you go outside of that, then it becomes unallowable and undesirable. Because if you have too much variation in your parts, and like size and things like that, then your parts don't fit together. So, and actually in reality, no two manufactured parts are exactly identical. So you have some degree of variation that exists at all times. So, so in order to describe that variation and describe what is acceptable variation, we use the term tolerances. Those are used in production drawings to control the processes that we use to manufacture, and also to control the variation between copies of the same part. And in particular, your tolerances are applied to mating parts. These are parts that go together, just like when you were making your puzzle cube, you mated parts together. That's the same thing that you do in manufacturing. Like anybody that makes a part, any product that you have that consists of more than one part, they had to consider tolerances. Even your smartphone, as you look at that, if you look at all the parts that go together with that, you had to figure out, okay, what's acceptable variation with these parts that go together. And one advantage of using tolerances is that you can use interchangeable parts. Now, large tolerances, they can affect the functionality of your part. You have to specify what those tolerances are to make sure that you have proper function of your parts. A small tolerance, that will affect the cost of the part. So cost generally increases with smaller tolerances. That means the tighter that you have to have something, the more exact that you have to have a part, the more expensive it is to make it, because it will require some very precise manufacturing. It will require some extra attention. So that means manpower for quality control with inspection. And that could be physical inspection on the part of a person, or you have to buy a machine that inspects the part that will decide if we accept or reject the part. So you don't want to specify a tolerance that's smaller than necessary, because it will make your parts more expensive. And then you have this term NSI or ASME. ANSI is what is that? American. Yeah, I know the American Society for Manufacturing Engineers. That's what ASME is. That's the standard standard Y 14.5. That says that specifically that each dimension shall have a tolerance except those dimensions specifically identified as reference, maximum, minimum, or stock. The tolerance may be applied directly to the dimension or indicated by a general note located in the title block of the drawing. So it's actually codified how we that we have to have tolerances. Let me go back here. I'm going to go to this slide here. It says tolerances. A tolerance is an acceptable amount of dimensional variation that will still allow an object to function correctly. On the right side there, you see a press, and that is an object that, or a machine that applies a lot of force in a downward direction. In order to make that press, though, you had to make sure that all those parts were mating and flush with each other when they should be, so that way it would function correctly. So tolerances. You have three basic tolerances that occur most often in working drawings, and they are, we'll look at those. You have limit dimensions, you have bilateral tolerances, and you have unilateral tolerances. Okay, so we'll talk about each one of these in just one at a time. But hopefully you're starting to notice and recognize some of the notation here. Like on the top right there, you see a hole specification. So let's talk about limit tolerances. All right. So notice you have, first off, there's your upper and lower limit for that particular dimension. Okay, so you've given, instead of saying this is what it needs to be, you're given the high end and the low end for that particular dimension. And so any size in between or equal to the upper limit and or the lower limit is acceptable. So in this case, the upper limit of that particular dimension is 0.126, and the lower limit for that dimension is 0.125. Elsewhere on the drawing, we would have the units. So in this case, in this particular case, we're not given the units, but if we were to see the whole drawing, we would be able to see the units. Okay, now a bilateral tolerance, this is a little bit different. Notation slightly different. If you'll notice, it has, you're given the basically the middle or the median of the tolerance, and then you're given the allowable, how much bigger and how much lower it can be. So plus or minus 0.003 is the top one, so it's 0.250 plus or minus 0.003. That would be the depth, right? And if you'll notice on the next one down, you have 1.5 plus or minus 0.0105 rather. So that's 1.5 plus or minus 0.05. Okay. And so that plus or minus is used to specify the allowable variation in the up or down direction. So the counterbore depth on that particular hole there is going to be 0.03 larger or smaller than 0.25. 0.003 larger or smaller than 0.25, and that whole location, if you notice there, is can be 0.05 larger or smaller than 1.5. So it could be 1.55 on the up end or 1.45 on the bottom end. And then you have this other concept of unilateral tolerance. So it can, in this case, there's how we express that tolerance. This provides allowable variation only in one direction. It's just like a British boy band, only in one direction, either larger or smaller. So in this case, you'll see plus 0.004 or minus 0. I experienced this particular specification when I was working with steel manufacturers. They would specify the thickness of their steel as plus 0.00 something minus 0. So for whatever reason, that's how that industry chose to use their specification. So they always basically manufactured to the low end and then allowed themselves some variation on the high end. So in this case, the hole diameter that we see here is going to be 0.5. And it can be plus 0.004 from there, but not smaller than 0.5. So the most it can be is 0.504. It can be 0.503 or 0.502 or 0.501 or anything small, with more decimals than that. But it cannot be less than 0.500. Now let's identify the type of tolerances displayed in red here. Okay, so you've got limit dimensions, bilateral or unilateral. Okay, so limit dimensions, okay, there's a unilateral tolerance there, right? Because it's plus 0.005 minus 0. Over here, you've got a bilateral tolerance because that's got a plus or minus there. Okay, and then I guess this would be a limit dimension right here because I've got the high end and the low end expressed on that particular tolerance there. So specified dimension, this is the target dimension for which the limits are calculated. So there's my specified dimension is, in this case, 1.5. That's going to be the distance from the center of that hole to the edge. Okay, and then my limits are the maximum and minimum sizes shown. So then I can do some math. Fortunately, it's just addition or subtraction. So my upper limit in this case is 1.55. That's going to be 1.50 plus that acceptable tolerance of 0.05 rather. And then my lower limit is going to be 1.45. That's 1.5 minus 0.05. Now your tolerance, so you had your specified specified dimension, and then now your tolerance. This is the total variance in the dimension, and it's equal to the difference between the upper and lower limits. Okay, so your tolerance here is going to be the upper limit minus the lower limit. So I've got a 0.10 tolerance. That means I've got that much acceptable variation in my dimension there. So to calculate your tolerance, this is just another way to look at it. Here's your specified dimension, and then your plus 0.05, and then your minus 0.05 to get to your upper limits and lower limits. So your tolerance is going to be 0.10 in this case. So yes, there's another term called general tolerances we need to understand. These are tolerances that are assumed if you don't have a specific tolerance that's given for dimension. So typical tolerances are specified based on the number of digits to the right of the decimal point in a dimension. So, and they would be shown on the drawing. So for angles, I might say give a general tolerance for the whole drawing. I might say for angles, the tolerance is plus or minus 0.5 degrees. I might say also that if you notice, here's the x point x. That means for linear dimensions, it's going to be plus or minus. So I would have well, this is bottom right here. These are general guidelines here. So I've got that plus or minus 0.020. For x point xx, that means that I'm going to have a plus or minus 0.010. And then x point xx, that means I'm going to have a plus or minus 0.005. These are generally accepted general tolerances for linear dimension. Okay, so if you'll notice down bottom left here, this is how it's specified on the drawing. So it'll vary from drawing to drawing how they use it, but the engineer has to specify what the general tolerances are. What's the generally accepted variation for a particular part. So you can draw something and come up with your specifications, your specified dimensions, but you also have to accept the fact there's going to be some variation. If you'll notice, this particular part right here is that drill block that you did a section, or you should have done a sectional view on earlier this week. So there's your specified dimension there. So what would be the acceptable dimension, acceptable variation? Well, I've got 3.00. So then my general tolerance that would apply would be right there in the red circle. X point XX plus or minus, that means that it's going to be, I can accept a plus or minus 0.010. So that means that it can go up or down by that much. So my upper limit here would be 3 plus 0.010. So that's 3.010. My lower limit would be 3 plus a negative 0.010, or 2.99. So then my tolerance is going to be my upper limit minus my lower limit. So it's going to be 3.01 minus 2.99, or 0.02. So that's how much wiggle room I have on that particular dimension. If something is out of tolerance, then it gets rejected. So that is where we call it a manufactured part is said to be out of tolerance if the part's not within specified limits. And then manufacturing facilities, they institute quality control measures to help ensure that the parts are within tolerance. So actually every manufacturing facility I've ever been in, they have a way of separating and segregating the non-conforming parts from the conforming parts. And so actually when I was working at Charbroil, whenever we had a a non-conforming part made, we ended up having to make a non-conforming quality report, also known as an NCQR. And we had to track down why that particular part was made to be not conforming to quality standards. And so that was a way to make sure that we helped prevent non-conforming quality from happening. And so it was like if there was a non-conforming quality report done in your department, then you had to conduct some level of root cause analysis to figure out why it happened, and then come up with an explanation of what you're going to do to prevent it from happening in the future. And then you have things. Now we're nearing the end of this particular presentation. We're going to talk about fit. Okay, now this was something that you kind of dealt with a little bit with your puzzle cube design. Some of you had some problems with it when you got to your actual production of your puzzle cube, when you were actually making it, because you didn't have, it might have fit on a theoretical basis when you were making it in Autodesk Inventor, but then when you went to actually put it together, you realized, oh wait, there's a lot of variation in how I made these parts, and they don't fit now. You're gonna have a sip of coffee here. All right, so you have different fits. Okay, so you can actually specify what fits you need to have. So a clearance fit, this limits the size of mating parts so that you will always be able to assemble the parts to fit them together. So there's always a clearance, which allows for mating parts to be assembled. You can have an interference fit. That makes it so that you have an interference always resulting when the mating parts are assembled, meaning there requires pressure rather to fit them. Or you might have a transition fit where you can sometimes have a clearance fit and then sometimes have an interference fit. Okay, now a clearance fit, this would be like if you wanted to have an axle going into a hole, this looks like an axle because we have that center line there, and that implies, and then we also have a diameter there, so that part, that rectangle on the left side that you're looking at, is actually a cylinder, and so it has to go into that hole, and when it goes into that hole, it has to fit. So that axle has to spin, has to be able to spin. So there's no rubbing going on there between those two parts when they fit. So in order for that clearance fit to happen, then I have to specify that diameter with that high end, that low end, so that the high end of that axle has to be 10.00, the low end has to be 9.92. And if you look at the high end and the low end for the hole, you'll notice that high end and the low end for the hole is bigger than the high end and low end for the axle. Those are always going to be cleared. Now this is an interference fit. In this case, you're always going to have an interference between the axle and the opening. So we flipped them around now. So I've got, in this case, the axle is always going to be bigger than the hole, which means that in order for that axle to go in, I'm going to have to apply a lot of pressure in order to, and it's going to cause the hole to expand, which means it's going to be a tight fit. And that may be in a situation where I want it to go in and I want it to stay in, or maybe I want there to be friction between those two parts. Okay, and then now I've got, let's look at a couple more definitions here. You have this term maximum material condition. That's the condition of a part where it contains the largest amount of material. And this would be a specification where I'd have the length of the plate having an upper dimension, or in this case, the maximum amount of material would be the diameter of the hole. It means that the lower limit of the dimension would be relative, or would correlate to the maximum material condition. So I've got more, and these correlate to cost, right? Because the more material I use, the more a part costs. Then you have least material condition. This is the condition when it contains the smallest amount of material, and this is an external feature. So the lowest least material condition of an external feature, so the length of a plate, that'd be the lower limit of the dimension, meaning that it can be no smaller than this. And then, or like a hole, the upper limit of the dimension. So the hole can be no bigger than this, because if it goes bigger, then I end up with less material than I need for this particular part. Maybe it'll end up being lighter than it needs to be, would be an example. So a lot of this all correlates to cost, and I'll get into that in a little bit. So allowance, that's the minimum clearance of, or maximum interference between the parts. So my allowance. So in this case, my allowance would be my minimum material condition minus my maximum material condition minus of the internal feature minus my maximum material condition of my external feature. So that's going to be 10.15 minus 10.00, and that works out to be 0.15. So that's how much that's how much of a allowance I have there. So since the smaller hole will result in the most material in the part, that's where the maximum material condition is on that particular item. And then on the axle, 10.00 is the maximum material condition, because that will result in the most material in the part. And so that's for your external and your internal features there. So in this case, my allowance is negative 0.15. So it works out to be negative, but I take the absolute value. So the allowance in this case is 0.5. So let's talk about dimension tolerances, and we're nearing the end here. So in general, the more significant figures in the dimension, the tighter the tolerance. So like where we see a lot of significant figures being used is in aerospace, aircraft manufacturing, or on the defense side, missile manufacturing, or making high-end drones, or Navy ships, or things like that. So the more significant figures, the tighter the tolerance, and overly precise dimensions. So if you specify a very precise dimension, that's going to mean then that you're going to need to have more sophisticated manufacturing equipment in order to manufacture that part. So you got to be careful if you are a designer, when you're making things that are going to be manufactured. You want to make sure that what you're speccing is the right size for what you're trying to build. So you only want to specify dimensions only to the precision and tolerance necessary for the part to function properly. So you don't want to use aircraft level manufacturing specs when you're only making a child's toy that doesn't need that level of tolerance. So this all relates to cost, and certainly if you go further in your engineering education, you're going to run into where you actually have to calculate the cost of adding more severe tolerances to your specifications. So that's something that's going to be down the pike for you as you go on in your engineering education. So at this point, I would normally ask for questions, but the only beings that I have in the room with me right now are dogs, and they can't talk. So if you have questions, please feel free to send a message to me by either in Canvas or by email, and I will try to get back to you as soon as possible. Thanks.